Venus beginning to rise. It's on the other side of the sun. You're Earth. You're all Earth. Every one of you. Maybe not. A few of you maybe not. But anyway. But now, where it is now.
Yeah, so first of all, thank you so much for the invitation to speak here today, and thank you all so much for coming out, even though it's cloudy. I was placing bets on how many would show up, and I figured that surely it wouldn't be packed, but I have a very nice audience today. Thank you. So today, we're going to talk about the moon and its mysterious ancient magnetism. So, as he introduced, I am a paleomagnetist, so I study how ancient magnetic fields are recorded in rocks, both on Earth as well as in space. And, what do you think is the oldest branch of science? Like, what is the oldest field of science that humans have investigated? Probably astronomy, right? You're in the right place. We've been looking up at the stars since the beginning of time. Well, I'm going to argue that paleomagnetism is actually the second oldest branch of science, even though you've never heard of it, probably. So, the magnetic compass was first invented in China about 2,400 years ago. And what they figured out was you could find deposits of this mineral magnetite that you could shape into a needle or spoon or whatever, and if you balanced it just so, it would point hundreds of years to help early explorers navigate, people who were conducting trade across the continents, even across the oceans, would use this magnetic compass to figure out which way was north. Star. They thought the star had some mystical force that was making the spoon or the needle go in that direction. And they had no idea what the truth was until this really intelligent breakthrough came through. And it was by a magnet, and it has this invisible magnetic field and field lines emanating from it. And what a compass needle is actually doing is it's aligning itself with the field lines of the Earth's magnetic field. And alas, the field of paleomagnetism, although messed around since 2,400 years ago, all of a sudden became an actual discipline in about 1600, whenever we tried to understand the Earth as the source of the field. So, it has a north pole and a south pole and field lines connecting them. And this magnetic field is generated by fluid motions in the Earth's core. And this field, the Earth's field, has been around as long as we have rocks that we think can reliably record the magnetic field. So what we have on the y-axis here, where is this? Okay. What we have on the y-axis is something called the virtual dipole moment. That's just another way of saying how strong is the, like, magnetization that would be produced by the field, if you were to observe it. And then on the going left and right here, what we have are different points in time. So in the recent time, like 1 to 300 million years ago, the Earth's magnetic field is like this strong. And if you go farther, today, but it was still there. So we have records of Earth's magnetic field for like 3.6 billion years. It's pretty crazy, and we can retrieve this from rocks using paleomagnetism. So ultimately, what generates the Earth's magnetic field is convection inside the Earth's core. So the Earth has a crust, that's what we're standing on. Underneath that is a mantle that's made out of silicate. And then at the center of our planet is a core made out of iron nickel. And part of the core is fluid on the outside portion. And over billions of years, the Earth's core has been cooling off. So in the liquid portion of the core, hot metal rises and cold metal falls. And it's that convection that propels heat loss of the core. But at the same time, you have this organized motion of a conducting fluid. And basically, you have big current loops forming inside the core. And whenever you have motion of conductors in an organized fashion, you can produce a magnetic field that sort of moves through the current loop. And it turns out that the Earth's core isn't just one current loop, it's all the current loops of all the fluid motions that are happening locally within the core. So you get something that looks like a tangled web of, where's the, oh, here it is, okay. A tangled web of magnetic field lines. And the fluid motions in the core can change over time, such that the directions of the north magnetic pole and the south magnetic pole can actually reverse on time scales of a few 100,000 years. And so what you see is at the center, at the core, the field lines are all garbled and messed up. They're in all these weird configurations. Well, whenever you get out to the surface of the Earth, it looks like a bar magnet where there's a clear north and a clear south. So all in all, we have a very good understanding of the Earth's magnetic field and its history, but what if we want to study magnetized fluid motion? So the fact that the body has a core tells us that early on in its history, it underwent large-scale melting, enough to separate metal from silicate and form a core in the first place. So that's one fundamental trait about a planet that we can learn from just observing a magnetic record. Another thing is it tells you is that there's some mechanism to sustain motion in the core, and that mechanism can be either convection, hot metal rising, cold metal falling. It can be chemical buoyancy. Maybe you have light metal in some parts of the core that want to move upwards and heavier metal that wants to move downwards, and that can also sustain convective motions. Or you could have something unusual going on. Maybe you have an outside force acting upon your planet that's shaking it up somehow. Maybe there's a big impact or tidal interactions with another planetary body. That can cause mechanical stirring of fluid in the core. So any one of these things can contribute to the generation of a magnetic field. And so far, paleomagnetists like me and other magnetism scientists have shown that magnetic fields are pretty common in the solar system, not just today, but also in the past. So the Earth, we are currently sitting in a magnetic field that is about 50 microtesla in strength. Mars used to have a magnetic field until about 4 billion years ago, and Mars's field died, and we're still not quite sure what knocked it out. It's kind of a mystery. Ganymede, which is one of Jupiter's moons, has a magnetic field today. It's a lot weaker than the Earth's, though. We're like 50 microtesla. Ganymede's at about 700 nanotesla. So that's about 100 times weaker-ish, a little less than 100 times weaker. Mercury has a 200 nanotesla magnetic field. And it turns out that we've done paleomagnetic studies of meteorites from asteroids, and we've even shown that some asteroids used to have magnetic fields in the very early solar system. So within about the first 100 million years after the solar system initially formed. And that was like 4.567 billion years ago. It's a great number to remember. It's super easy. And the moon is an interesting target for understanding planetary magnetism because it's actually in this kind of in-between size range where it's smaller than the planets like Mercury and Earth that still have magnetic fields today, but it's bigger than asteroids, which would have had extremely short-lived magnetic fields that would have gone extinct. So we like learning about the moon's magnetism because it's sort of a natural laboratory for understanding this, transition size range. And so, well, what are the big questions about the moon and its magnetism? Well, first of all, we know that the moon does not have an internally generated magnetic field today, like the Earth does. All right. We can tell that because we've sent spacecraft to the moon to look for it, and it's not there. But the questions are, did it generate a magnetic field in the past? And if it did, all right, how strong was that field? What powered the field? And how long did that field last? So our first inkling of lunar magnetism came in sort of this early lunar exploration phase. So whenever the Apollo missions went to the moon, they took these magnetometers to the moon with them. And so here is one of their magnetometers that they just plunked down on the lunar surface. And it measured how strong the magnetic field was in that one spot, wherever they put the magnetometer. And, depending on which Apollo landing site you landed at Apollo 15, the field a couple hundred nanotesla. So there was quite a bit of variation, but all of these numbers are way weaker than the Earth's current magnetic field. But they're not zero either. So this was like a hint that the moon may have had something magnetic going on in the past, but it isn't there anymore, but the rocks record it in their memory. And we've since sent spacecraft to the moon again. We've sent the Lunar Prospector spacecraft. Japan has sent a spacecraft called Kaguya, and they've made magnetic maps of the moon from orbit. And so the bright colors like blue, red, and green, those are where the lunar magnetic fields in the crust are the strongest. That's what's remembered from a previous magnetic era. But you see that there's a few places with very strong magnetizations. That would be like the red. But then most of it is not very magnetized at all. So it's kind of mysterious why magnetism is not homogeneous across the planetary body, or what the origin of the fields that initially magnetized these rocks was. So we had to do a little more work. And luckily, this was made easier by the fact that the Apollo astronauts, starting with Neil Armstrong and ending with Apollo 17, someone like Jack Schmitt, they collected hundreds of moon rocks for people like me to geek out on. And so during the Apollo era, there was an initial wave of paleomagnetists like me who started to measure the magnetism in the moon rocks to figure out the early magnetic record. So in order to understand what we do and how we study these rocks, I'm just going to kind of go over some background of how rocks become magnetized and how we can retrieve their magnetic records later. So what happens when rocks form, especially igneous rocks? So igneous rocks are rocks like lava flows, basaltic rocks, like in Hawaii. You have a volcano erupt and it dumps lava and it cools down and it freezes, right? Okay, so whenever an igneous rock forms, it starts out really hot, and it starts out above the magnetic recording temperature of little individual magnetic minerals and rocks, and that's called the Curie temperature. So you start out hot, and whenever you're above the Curie temperature, the magnetism in a rock is random because there's so much thermal energy and thermal fluctuations that you can't record any particular direction. But if there's an ambient field around whenever the rock is cooling as it's forming, what happens is the magnetic grains in the rocks will have a bias towards acquiring magnetism in the direction of whatever field is around. So that is a direction that is retained in the rock even after the field goes away. And it's a semi-permanent magnetization that sticks around. If there's a weaker magnetic field, this process becomes less efficient, so you'll still have some grains that are magnetized in the field direction, but some grains will not be. So you'll have some biasing, but not a total biasing. If there's no magnetic field present, then there's nothing to bias the magnetic directions in grains, and so the resulting magnetization will be random. So what you end up with is, if there's a field around, the magnetism direction in the rock will be aligned toward whatever field was there at the time that the rock formed, and the strength of the magnetization is directly proportional to the strength of the field that was there. So that's how we can figure out how strong the fields used to be. And what we're looking for in a rock whenever we study its magnetism is the magnetism in a rock is recorded as a direction, and it also has an intensity. So if you've ever taken physics, it's a vector. So whenever we take a rock in the lab, we initially measure what's called its natural remnant magnetization. That's what's naturally in the rock before we mess with it by doing experiments on it. So we initially measure that. And you can imagine that a rock is an assemblage of magnetic grains inside it. And some grains, like the red ones here, are hard to remagnetize. It's hard to mess with the magnetism in those grains. And some grains, like the blue ones on the screen, are easy to remagnetize. And sometimes those easy to remagnetize grains can get overprinted by contamination. So let's say, someone used a magnetic tool to sample the rock, or someone took the rock too close to their laptop computer or whatever. So we want to make sure that we remove these secondary contaminations. So what we do is we start to use different techniques to demagnetize each rock in the lab. And we stepwise remove contaminating fields by heating them in an oven until we reach the Curie temperature. And so you can start out with you can start out by removing overprints from the rock until you have eliminated any contaminants. And whenever that overprint, that's the blue contamination line here, whenever that's removed, you'll just have the original magnetism in the rock that decays towards the origin, decays to zero. And that is what we're looking for if we want to see that a rock contains an original magnetic record from the moon. So the early paleomagnetists, and when I say early, I define it loosely as before 2009. It's a bad way to say early, but that was sort of the initial wave of studies, and things have really changed in the last 10 years. Starting in the Apollo era, people measured the magnetism in rocks. They did that demagnetization experiment that I just showed on the previous slide, and they figured out which rocks had some magnetism in them. And they also figured out the paleo intensity. And that paleo intensity, that word means the strength of the field that was around at the time the rocks formed, okay? And they figured this out for a bunch of lunar samples. So each dot is a lunar sample on the screen. And on here, the x-axis is the age that that lunar rock formed. And so what we broadly see is that we don't have much data before 4 billion years ago. All right. But then between like 3.5 and 4 billion years ago, there's a lot of scatter. You have some data points where the field strength was almost zero, and you have some data points where the field strength was like over twice as strong as the Earth's magnetic field is today. So that was weird. We didn't really understand what was going on. We also know there's no magnetic field today, but we also have non-zero intensity values like yesterday, basically. So this whole plot was kind of suspicious, and we weren't sure what was happening. We weren't sure if they were accounting for overprints or secondary contaminants properly. We weren't sure if all the ages of the samples were correct. Some of them may not have been dated properly. And so even beyond that, this plot, according to basic physics, did not seem possible for a few reasons. So some of the mysteries that were there were, okay, first of all, we have no idea what happened on the earliest moon because we don't have any data. So we don't know if there was a lunar dynamo. A dynamo is the word for an internally generated magnetic field or not. So there's models for how quickly the moon would have cooled off because it's a smaller body than the Earth. It would have cooled off faster than the Earth did. And so, according to the models, the moon would have cooled off so fast that you could not have generated a magnetic field via thermal convection of the core after 4 billion years ago. But we have all these dots after 4 billion years ago. So that was weird. And then there's also these scaling laws that say how strong a lunar magnetic field could ever be. And even in the most generous application of that, you cannot have fields stronger than like 20 microtesla, but we have dots that are higher than that too. So really there was a lot about this Apollo era plot that was not making sense. And this merited a revisiting of lunar magnetism. So unresolved at the end of the Apollo era, we still didn't know for sure whether there were actually substantial magnetic fields on the ancient moon or whether we were seeing some kind of errant contamination in the rocks. We didn't know what caused the magnetic fields if they were there. Are they from a lunar dynamo, an internally generated magnetic field? Or it's also possible that during the time when there were lots of large impacts happening on the moon, like more than 3.5 billion years ago, those impacts would like vaporize rocks and create plasmas. And it turned out that the motion of plasma can also generate transient magnetic fields that last for up to a day. Depending on the size of the impact. Very small one, it'll just be like less than a second. But still, that was a hypothesis. And then if it turned out that the moon did have an internally generated magnetic field, like what produced it? What was the power source? And how long did it actually last? Did it last till like 200 million years ago, like that dot on the plot showed? Who knows? We had to answer those questions. And so that's kind of where I stepped in about 2009. Incidentally. It was coincidence that that date was there. So anyway, so what we do is I'm very lucky. I actually get to go to Johnson Space Center. So I get to go to the Lunar Receiving Laboratory. This is where they have stored pretty much all of the rocks from the Apollo missions. And it's pretty intense. You have to wear a bunny suit and cover up everything, and then you still can't like touch the rocks even though you're wearing a clean room suit. You have to put a glove on your suit, and then you have to put your arms through these like biohazard type of like containers. So you got to stick your arms in this chamber, and then you also have to put gloves on your gloved hand. So there are 3 layers of gloves if you want to pick up a moon rock on the inside, and it is really hard to manipulate them that way, as you can imagine. So it's a pretty crazy experience, but ultimately, you know, I go there and I convince NASA to actually give me something. And so, you know, you might start out with a rock that's that big, you know, something like a little smaller than your head maybe. And so this is an example of a slice of rock that I studied when I was at Johnson Space Center. So I got a slab, it was like this big. In their lab. And so that little cube down there is 1 centimeter in width. And then what happens is NASA doesn't give me all of that because it's way too precious, right? They can't spare that on just one person. So they give me little chips of it. And again, each cube is 1 centimeter, so you can see the size of what I have to work with. So based on something that small, I will make grand conclusions about an entire planetary body. Yep.
I'm sorry, I have a question. Did the astronauts take a lot of notes or photographs when they brought the rocks back so that you could maybe figure out the orientation of the magnetic field and its particular strength?
That's a very good question. So it turned out that most rocks that they picked up were just lying on the surface because they'd been hit by an impact at some point. And so they didn't have their like original orientation. And that's like 99% of the rocks they picked up, maybe more than 99%. There are a few rocks that might be from in-place outcrops or in-place boulders, and they are well photographed, and we are trying to reconstruct their magnetism direction from that. And so far it is promising, but I'm not going to give away the spoilers just yet, right? So anyways, I get this little tiny amount of stuff, and then I bring it to my lab. So this is my paleomagnetism laboratory at Rutgers, and so I have on the left a clean room because you don't want the moon rocks getting all mucked up by all the earth rock stuff and getting materials mixed up and dirty. And then on the right, there's this like aluminum frame looking thing. So that thing is surrounding my magnetometer. So what happens is I put the rock on the magnetometer and I lower it into this machine, and it measures the magnetic direction and intensity in the rock. And then as I do a demagnetization experiment, I have to like, you know, heat it and then put it back down and heat it and put it back down like a bunch of times. But so an experiment could take anywhere between like hours to weeks, depending on how crazy I'm trying to be. And so what happened with this particular rock that I showed you on the previous slide was on the right panel, here is an example of what a demagnetization plot looks like. So the first dot up here is the natural remnant magnetization. That's what's in the sample before I heated it. And then I stepwise heated it. So the mouse is kind of funny whenever. Yeah, okay, so that's the initial point. And then I heated it to 50, 250, 560 degrees C, 600 degrees C, 640 degrees C, all the way down 660 degrees C. And so the point is, the Curie temperature of iron nickel is like 780 for pure iron, and then as you add nickel to it, it gets lower. So probably for this rock, it was around 660 degrees C, because it had some nickel in it to lower the Curie temperature. So what happened was I found this vector that goes to the origin, so that means that this rock is magnetized, and it acquired that magnetism on the moon at the time that it formed. Some overprint on Earth would have been removed by like 200 degrees. It wouldn't have stuck to that highest temperature. And then we did this other experiment to figure out the intensity of the field that initially magnetized the rock. So what we do is, as we demagnetize the sample, after each heating step, we also heat the sample a second time in the presence of a laboratory field that is known. So I might demagnetize the rock in a 0 field and then heat it again in a field of, say, like 5 microtesla or whatever. And so the slope of how much magnetism is remaining after each heating step versus how much magnetism is gained at each heating step, the slope here for the green dots tells us how strong the ancient magnetic field was. So basically, the ancient magnetization over the lab field is equal to the ancient magnetization over the laboratory magnetization is equal to the strength of the ancient field over the strength of the lab field. So what we figured out was the field that was recorded in this rock was actually 5 microtesla, which is 10 times weaker than the Earth's current magnetic field, but pretty strong for a moon. You know, it's not 0. So that was pretty cool. And I'm not the only person who's worked on this. It's a bunch of labs, but together we've been able to assemble a record of lunar field intensities over time and revisit that Apollo era data. And what we found is actually those strong fields early on in lunar history, between 4 and 3.5 billion years ago, are correct. Which is crazy. We've reproduced them in the modern studies. We haven't found as much scatter, so maybe we need to revisit some more samples and see if the scatter is still there or whether it really did go away. And then we don't have much data between like 3.2 and like 2.5 billion years ago, but I have this one sample that was like somewhere between 2.5 and 1 billion years old. It was hard to date properly. But regardless, we have a magnetic field on the moon that lasted for at least 2 billion years, which is crazy for something that small. But it's real, and it's cool. So, and we also have some new data points that aren't published yet, so they're kind of flashing up in red there. All right, but the question is, how could the moon have generated such a long-lived magnetic field as such a small body? Well, first of all, you need a core. The fact that we have a lunar magnetism implies there is a core, but we had yet to observe it for a long time. But in the last decade, seismologists have processed some Apollo seismometer data and using some very nice mathematical filtering techniques. And they think that they have found evidence from seismic velocity changes inside the moon that, okay, maybe there is a fluid outer core and a solid inner core inside the moon. So maybe the fluid outer core could have generated a magnetic field at some point in the past. So we think the lunar core was probably less than 400 kilometers in radius. Note that the moon is like 1,700 kilometers in radius, so it's a small fraction of the moon's overall size. The Earth's core is about half, of our radius, so just for comparison. All right, so now that we have a core, we have to think of what could have powered the magnetic field. We already talked about convective dynamos earlier. You can have a thermal convection, hot metal rising, cold metal falling. You could have thermochemical convection once the solid inner core starts to freeze. So the core's cooling over time, and eventually it's under pressure. It's going to cool off enough to make iron solid sometime. So once that solid iron freezes out, the rest of the liquid ends up having more light elements in it, like sulfur. These are things that were alloyed into the iron in the first place. Those like to move up. So you have this chemical buoyancy of moving light elements up that could have also contributed to fluid motions in the core. But the moon also has opportunities for these exotic dynamo mechanisms. So there's a couple mechanical dynamo options for the moon that have been proposed. One is that giant impacts could have hit the moon, and that would have caused the moon to shake, like boom, boom, boom. It's just kind of like resonating after each large impact. And that shaking could have actually, stirred up fluids in the core to generate a magnetic field. But that effect only lasts as long as there are giant impacts occurring on the moon, and we think those stopped at about 3.7 billion years ago. So that doesn't explain like the young lunar magnetic record after that. But then there's this other option called precession. So the idea behind this one was, how many of you know that the moon's moving away from us? Yeah, okay, good, cool. So back then, the moon was much closer to the Earth than it is today. And as a result, Earth's gravity was pulling on the lunar mantle more strongly than it does today. And so the moon isn't a perfect sphere. It's actually oblate a little bit. Hard to see, but it's true. It's like a football. Not that exaggerated, but you get the idea. And so what happened was, not only was it oblate, but it was also tilted more with respect to the Earth. So its axial tilt, its obliquity was higher. So what happened was, at this time, the Earth's gravity was sort of pulling the lunar mantle kind of into its orbital plane, because it was tilted, so it was trying to yank on the mantle. And so this was actually causing the moon to shake a little bit. And this shaking caused the mantle of the moon and the core of the moon to spin around different axes. I know that sounds funny, because it's all happening in the interior of the body, but it was causing this differential rotation. And as a result, you can imagine that if I swish my water bottle around, so I'm moving my bottle, let's say that's the mantle of the moon, and then I have the fluid of the core, that's my water. You see how the water is sloshing around when I move the bottle, right? So it's kind of the same thing. So you could generate a magnetic field from that. And so each one of these mechanisms has a different predicted lifetime. Thermal convection pewters out pretty quickly. Impacts also pewter out pretty quickly. But precession, according to the lunar migration rate models, could have actually lasted for a very long time, as could have thermochemical convection. So we sort of have two plausible models for what could have generated the field to last for so long, one of these two. But the issue still in lunar magnetism is that there doesn't seem to be enough power to at least explain the highest, yeah?
What about tidal forces from the Earth and the Sun?
Yeah, so the sun's not strong enough to cause this much turbulence in the moon. So the Earth's tidal forces are actually kind of part of this precession dynamo discussion. And so yes, it helps, and it feeds into this precession model that I was talking about. But yeah, it is being considered.
I was thinking it just might slow the cooling.
Oh, because it's adding heat to the system? Yeah, that's correct. Yeah. But it can't be all of the contribution, basically. So what people have done is they've just estimated what is the maximum possible energy budget that could be helping the lunar core generate a magnetic field. And there's different things that can contribute to the lunar energy budget. One is just thermal energy from cooling off since the moon initially formed. That's what's in the orange there. Then once you have the inner core starting to crystallize on the moon, that has some gravitational energy and also releases some heat. That's called latent heat. That's released whenever material solidifies. And then we also think that the lunar core might have gotten some radioactive elements included in it whenever it formed. Maybe there were some radioactive elements in the metal. And so we were trying to figure out how much radioactive heat could have been produced as time went on. And so it turned out that if you just consider thermal energy and gravitational energy, you could power a weak 5 microtesla dynamo for pretty much all of lunar history. That's the bottom line on this plot. Okay, and if you wanted to produce a field that just explained that high field period, that was 300 million years between like 3.8 and 3.5 billion years ago, yeah, you could produce an 11 microtesla field for 300 million years using, thermal energy and gravitational energy. And if you included radioactivity, accounting for like the maximum possible radioactive heat budget for the moon, you could get a 23 microtesla field for 300 million years. But to get a 50 microtesla field, something higher, you'd have to have all of this plus 12 times the maximum possible radioactive heat budget of the moon. So right now it's not possible from just internal sources, which is again lending credence to this idea of the precession dynamo and the tidal influences from the Earth. Because just the moon on its own doesn't have enough punch to pull this off. But all in all, we managed to show that the moon did have a magnetic field with quite a long lifetime, from at least 4.25 to at least 2.5 billion years ago. The field of the Earth, we don't know when it started, but it's had one from about at least 3.5 billion years ago until now. Mars had one for a few 100 million years. Asteroids had very short-lived magnetic fields, but they did have them in many cases. So what we see is that, the moon is intermediate in size to the Earth and asteroids, but it might have also had an intermediate field longevity, which is kind of cool. And so all in all, our conclusions in lunar magnetism say that the moon did generate a long-lived magnetic field. There's some preliminary data, which is not published yet, so I'm not going to go away too many details. It's not my study, but the dynamo probably died by about 1 billion years ago. The magnetic fields that we're retrieving are stronger than theoretical predictions for convective dynamos, which means that you might need a more energetic and long-lived power source that could be precession and tidal forcing, that could be inner core crystallization helping contribute through buoyancy or latent heat or whatever. Or maybe there's something we haven't thought of yet. There's a study that came out this year that says maybe the mantle of the moon didn't freeze completely into a solid body, and there was some magma ocean at the base of the mantle that might have been convecting and generated a magnetic field, and no one had ever proposed that before. And we have no idea how conductive silicate magma could be, so it's kind of a pie-in-the-sky idea, but maybe that is the type of idea we need to think about. So all in all, we have a cool problem to work on, and I think we have plenty to keep working on for the next, 40 years, kind of like the astronauts started us out with. All right, so thank you so much for coming out, and I'm happy to answer any questions.
Yes, was there any interaction between the Earth's magnetic field and the moon's magnetic field?
That's a good question. So dipole magnetic fields, their strength falls off as 1 over radius cubed. So by the time you get to the moon's distance, even back then, the maximum field strength is like a few nanotesla. So that's nowhere near the intensities that we're inferring. And even like the sun's magnetic field, the galactic magnetic field, all of this is all nanoteslas. So it really has to be from the moon.
One of the more current theories is that there was a collision of Earth that created the moon. Has that been a consideration at all in determining that?
So actually the moon forming impact is important in that it causes the moon to form initially under hot conditions. And so that also helps the moon have a core at the beginning and to also have a lot of heat at the beginning, which would have had to escape the body by cooling over time. And so yes, the hot origin of the moon through this giant impact like helps us have a core, and it helps us generate a magnetic field from just thermal convection in the first place. Yep.
Just a question about the samples. I don't know much about the moon rocks. Were they all gathered from one area of the moon, and is there any chance that any of that is not originally from the moon?
Good question. So we have samples from all the Apollo landing sites. So Apollo 11, 12, 13 didn't make it, in case you haven't heard that story. 14, 15, 16, and 17. Okay, so they're all on the near side of the moon, so that's the side that faces us, and they're all like mostly within about 30 degrees of the equator, because that's the easiest to communicate with Earth and, you know, all of that. So the issue is, yeah, we have a little bit of a biased sample selection in that they're all from the near side of the moon. And it's only safe to land on like smooth areas, right? They didn't want anything too hilly or bumpy, so we had a tendency to land near these lava flows. So that's where like most of our rocks came from. And so yeah, there is some biasing there. And if you look at the kind of Apollo sample record that on the older data slide, you saw that there were these big gaps in time. Like we had like hundreds of millions of years chunks where we didn't get any samples that were that old. And part of that's because like you land in one place and all the rocks there are the same age as each other. So all the Apollo 11 and 17 rocks, the basalts, they're all like 3.5 to 3.8 billion years old. They're all in this 300 million year range. Apollo 15, all the rocks are like 3.3 billion years old. Apollo 12, all the rocks are like 3.2 billion years old. Apollo 14 and 16 are all impact melt rocks from the big bombardment phase in lunar history, and they're all 3.9 billion years old. So yeah, we have a problem with that, which is why we need to go back to the moon. Yep.
In the absence of the moon having any magnetic field, could the sun have had some influence on it with massive storms in the early formation days?
So, you mean like coronal mass ejections and
Right.
solar flares? Yeah, I mean, they do emit, you know, from time to time. Their strength is still not high enough to cause microteslas. Yeah.
Could you talk a little bit about the oriented specimens?
Yes. Yeah, so there's a few different ways you can try to orient rocks. So one is to look for a fabric in the rock. So basically the idea is when a lava flow flows, it's moving horizontally across the surface. And that causes like crystals in the rock to align with that horizontal direction. And so you can look for that horizontal plane in a few different ways. You can use a magnetic technique called susceptibility to find it, or you can use just like the shapes of grains and kind of like cut a three-dimensional cross-section of the rock and like calculate that. And so some people tried to do it that way, and they found an inclination of the magnetic field that would be consistent with an axial dipole, so like a north pole at the moon's north pole and a south pole at the moon's south pole. So it was like within some error bars of that, so it was plausible, and that was just from like 3 samples that they could do that on. And then more recently, what people have tried to do is to look at photos of rocks collected on the moon by the Apollo astronauts. And this is tricky because like whenever we collect paleomag samples on Earth, we keep track of the direction of the orientation of the rocks by what the Earth's magnetic field is now. Like we drill a core and then we have a compass, and that helps us orient the core that we just drilled. Well, we couldn't do that on the moon because there was no magnetic field to help us, right? So we had to come up with some other way to get orientations. So what they did was they used the photos, and they were able to use the sunlight angles, and they know exactly what time every sample was collected. They know exactly where each sample was collected, And so you can do a bunch of magic by like taking the rock at Johnson Space Center and then kind of like taking photos of it and aligning those photos with how you can see it on the parent boulder on the surface. And there's a lot of trigonometry involved, as you can imagine, lots of angle rotations and constraints. But yes, it is possible to orient a handful of samples, mostly from Apollo 17, and mostly because Jack Schmitt, the astronaut who collected them, is still around and somehow has a very good memory of every single rock he collected, which is amazing. So by talking to that astronaut directly and also using the sunlight angles and stuff, we're able to pick a few samples that this is possible on. And so earlier this year in March, there was a student from MIT who presented an oriented magnetic measurement that was also consistent with an axial dipole. So there are a few studies that, you know, are giving us a hint as to what the geometry would be. So that's cool. Whenever you use these sunlight arguments to get an orientation, there is a risk that the boulder that you think is a rock that's in place might not be in place. You could imagine there's a big impact that just picked up a huge chunk and just like chucked it somewhere, right? So we're not completely sure, but it's kind of the best we can do. But another way to assess field geometry is to look at these kind of crustal math in different ways. So really the samples are the most reliable way to do it. Yep.
How did you get into this field?
So yeah, when I went to college, I thought I was going to be a math major, like everybody at Caltech. And so I started out in college, and I got really bored doing proofs pretty quickly, but I noticed there were all these geology majors that were like going on field trips and like going to Australia and South Africa and China, and I was like, I want to get in on that. I don't want to be stuck inside. So I changed my major to geology before I had ever been camping before, which was a questionable decision, right? And I had also never taken an earth science class before, but it just looked so cool. And so, yeah, and then I got super into it once I actually started taking classes in it. And I'd always been interested in space. I was like you. I would go to these astronomy club meetings when I was in high school and, you know, kind of like learn about stuff. But that's mostly stars, right, and galaxies. Didn't have much in planets. And geology got me really interested in planets. And so I did some undergraduate research in paleomagnetism with a professor at Caltech. And I really liked magnetism. I thought it was like this sneaky way that you could learn about the properties of the Earth's history. And it's like invisible. You can't see it, right? But it's there and it's cool. But I always wanted to work on planets. I wanted to do space stuff. I couldn't shake the space thing, you know? And so whenever I wanted to apply to grad school, I asked around. I'm like, I want to do magnetism, but I want to do space. And then I was talking to this guy who's actually he has the office next to me at Rutgers now. Funny story. So he was a grad student at Caltech, and he's like, you know, there's a lab that does that. And that was at MIT. And so I applied to MIT to work in this lab with Ben Weiss, who was the first person on my acknowledgement slide. And I got in, and I started working on lunar magnetism then. And it's been a great ride, and I don't just work on the moon now. I work on meteorites, I work on impact craters, as he mentioned at the beginning of the talk, and it's been a lot of fun. But, you know, it all started out by me hating proofs. Yep.
You mentioned that we've seen asteroids with recorded magnetic fields. Does that all come from just impacts or like interference with larger bodies? I can't imagine they have cores or anything.
So we've managed to show that they did have core dynamos, which is pretty cool. So if it's an asteroid that was big enough to undergo melting and actually differentiate and form a core and a mantle, like you could imagine that like that core has to cool down. And so there will be like convection. And since it's such a small body, that convection will be rapid and you'll have like very pronounced fluid motions. So it's actually predicted that asteroid magnetic fields are like stronger than magnetic fields on the Earth. And especially because the field strength falls off as radius cubed, you could imagine you're much closer to the source on an asteroid. So again, you could have fields of hundreds of microteslas on asteroids. So it's almost expected. If you form a core, like you'll have a field like for some amount of time, probably. Yep.
So over 3 billion years, what kind of mechanisms are there through radiative damage or something like that, or crystal dopant migrations, anything that would decrease or increase the magnetization, such that kind of your
Like
your
a
assumption
space
that
weathering
the way
effect?
it magnetizes now is the way it would magnetize when it originally formed? Is there any?
So there isn't really a way to like significantly demagnetize the samples. Rocks can like lose their magnetism over time, but there's like a time-temperature relationship. So you'd really have to heat up rocks to a very high temperature to remove a substantial amount of magnetism. There is space weathering that creates like nanophase iron at the surface of rocks, okay? But whenever we study these, we're aware of that. And so we only sample the interiors of each rock to avoid that. And another thing that can happen, we've seen this in some samples, is that let's say you have an impact nearby and it melts some rocks and like splashes the glass on the surface of yours. And this is actually pretty common on the moon to have impact glass splatters on top of your rock. And yeah, that'll thermally demagnetize like the outside portion of the rock where that glass landed, you know, assuming that glass formed after the dynamo died, which in most of these cases it did. So yeah, I mean, there are a few things, but we also like are very careful whenever we select which region of a rock to analyze to sort of exclude that. Yep.
Would a magnetism in, say, a rock form better if it was a very strong magnetic field that cooled quickly versus a slower cooling with a weaker magnetic field? Is there any preference that it creates a stronger magnetic field in a rock?
The strength of the magnetization itself is, I'd say, like, it depends on your definition of quickly versus slow. Like, if you're looking at, like, millions of years versus, like, a few minutes, or billions of years versus a few minutes, okay, yeah. If you're looking at, like, a few minutes versus a week, not actually that much, you know? So it's this, like, interesting time-temperature relationship.
So you discussed various possibilities as to why the dynamo exists and how it's like shifting over the course of time. So what are the methods you're going to be using to test which one of them is actually correct, which one of them applies? Yeah,
so part of this starts to become not my particular job and goes to my collaborators, right? So the best I can do is to keep providing paleo intensity estimates for different points in time, because that's what I do. But then I have collaborators who actually model, you know, different scenarios, and then they make predictions for intensities. So really the way you test the difference is to find a technique that can make a 50 microtesla field, you know? And so people work on that. Like, there's people modeling like how the fluid flows in the lunar core would have happened as a result of precession and tidal forcing, or how would fluid flows in the core have happened after a giant impact, you know? And it's those people's jobs. And so whenever they can create a model that matches the observations, then that's how we like filter through these things. And this is like a field of active research right now. Yep.
Hopefully this one's much simpler than what you've been talking about. But it's my understanding there's a giant chunk of lodestone in Canada that makes the magnetic field, which is, I guess, the combination of the dynamo and the lodestone is kind of the net of the whole thing. Not really lined up with Polaris.
Yes.
And has been that way for a long time, although there's wobbling and all kinds of stuff going on. And so that's, so really the magnetic record is reflecting a couple of different factors.
Right, so if you have, so lodestone is special because it's like really, really strongly magnetic, right? So it's magnetic enough to cause a deflection in what's observed. You have the lodestone field plus the Earth's geomagnetic field, okay? So yes, we take this into account actually whenever we sample on Earth, because we know there are super strongly magnetized rocks, and so we also use a sun compass sometimes on Earth when we collect samples to account for the fact that you could have very strong rocks nearby. On the moon, you could also have strongly magnetized rocks nearby. However, based on all the samples we have brought back from the Apollo missions, they're not iron-rich enough to really cause that much deflection. Like, the strength of the magnetic moment in a moon rock is something like at least 3 or 4 orders of magnitude weaker than a terrestrial basalt, from my measurements, for the same amount of mass. So,
is there any evidence of magnetic reversals on any other body?
I think, so this is a very new magnetic technique, but it's too complicated to explain how they do it, but they think they can find some magnetic reversals recorded in iron meteorites. And this is like super niche-y, but the idea is, have you ever seen an iron meteorite? Do you know what they look like? Like if you cut them and then you polish their face and you see these like Widmanstätten patterns, which are intergrowths of like low nickel iron and slightly higher nickel iron. And so it turns out that kind of in the boundaries between some of these grains, there are these, there's metal, and then inside there's these nanoscale size islands of a mineral called tetrataenite. This is super technical. But the idea is that even on the scale of like a millimeter or less, you can see like magnetic reversals in just these little tetrataenite islands, like little layers of them. And you can see the field like changing from like one layer to the next layer. And this is all like, it's like a new technique. It's called nano-paleomagnetism. So it's super cool. But yeah, I think that this has been observed. It's not for sure like how, there's some dispute as to how real the signal is, or whether you could have some like magnetic interactions between like these grains inside this meteorite. So it's a little tricky, but it has been posited to be observed. But these would be from like asteroids, right? We don't have enough data from the moon to assess. And the Earth is really the only planetary body we have enough data to like confidently resolve reversals. But I will say that every dynamo simulation that you ever run for anything always has reversals spontaneously happening. So they are like a necessary and like natural outcome of dynamo process, no matter what.
The sun does it every...
Yeah, the sun's reverses too.
15 or I forget, 7 years.
Yeah, so like magnetic field reversals, like if there's a dynamo, it will reverse. And it's just a completely natural outcome. Yep.
So how do we learn about the dynamos and you said Mercury, I think, and Ganymede? I mean, we don't have samples, do we?
We don't, but we've sent spacecraft there. So so we have like the Messenger spacecraft, for example, that went to Mercury, and before I think there was Magellan as well a long time ago. And so we've been able to measure the magnetic field, and Messenger actually like orbited around Mercury a lot, so we can have lots of different passes, and they can like, isolate the field geometry and also measure crustal magnetism there as well. Ganymede, they kind of were able to study using Galileo back then.
And so Venus is the only inner planet that doesn't have one?
Correct.
Do
Yes.
you know anything about it?
Yeah, so there's some hypotheses for why Venus doesn't have one. So there's a couple things. So one, Venus is like really hot. Like, so any spacecraft we've ever sent to Venus, and actually Russia is the only country that's ever tried to land, it lasted between like seconds and maybe like less than an hour, before it all melted down. It's so hot. So as I mentioned, one thing you really need to generate a dynamo is cooling of your planets. And you have to have a thermal gradient. Like if everything is hot, the core is not going to convect, right? So the idea is you don't have enough of a thermal gradient within Venus to sustain a dynamo. The other thing that's different about Venus is it's an extremely slow rotator. So it may not rotate quickly enough for fluid motions in the core to organize properly. So it's kind of a double whammy with Venus. Question? Yeah.
What will happen if there is no magnetic field in there?
What would happen if there's no
Or
magnetic field?
in time, it will take billions of years. for
Yeah, I
it to
mean,
be-
I think the Earth's gonna go kaput before our magnetic field will, really, because the sun will die. But the general idea here is magnetic fields are a nice shield, because basically, like, charged particles from the sun tend to get trapped along field lines and travel along them, so it kind of deflects a lot of charged particles from the sun. And if there was no field, those particles would interact with our atmosphere, and they would cause the atmosphere to, some gases in the atmosphere to sort of dissociate. So one of the hypotheses for why Mars lost all its water is that its magnetic field died, and then like these charged particles in UV could also like hit H2O, and then you get OH, and it knocks off an H, and because hydrogen is super light, it like flies away, and this is called hydrogen escape. So over a long period of time, you could have hydrogen escaping, and you would like slowly reduce the amount of water you had on your body, yeah, on your planetary body. And then also, it's been hypothesized that like cancer rates might be a little bit higher because you'd have a little bit more radiation, like, you know, making its way in to us. But I will say there's on Mars, it's easier to lose water and hydrogen because it's a smaller body, right? It has less gravity. The Earth is much larger, so even though we would have like hydrogen escape and stuff, it wouldn't be nearly as fast as on Mars. So it wouldn't be like the end of the world. It's not like the movie The Core, you know, it's like, but actually it would be bad for technology though, because the Earth's magnetic field kind of helps shield our communication satellites and GPS satellites and stuff. And so if there was like a solar flare or a coronal mass ejection, that would totally fry our electronics, and our modern infrastructure would have issues in that case, like all of telecommunications as we currently know it might have some problems. So I guess like the short answer is we'd still be alive, but we might be dealing with some like societal interruptions as a result. Yeah.
When the Earth's magnetic field flips, does it go to zero and then start up again, or does it just rotate around? Because that deals with the same issue. Of
It weakens. Yeah, it weakens, and then it kind of like gets stronger again. But what happens is like, so whenever I've talked about the magnetic field, I talk about it as a dipole, but it's a dipole at the surface. If you go to the core, it's multipolar. It's like a mix of higher order terms. So what happens during a reversal is you're transitioning from a dipolar strength state to like a multipolar state, and then back to sort of a dipolar state. And so yeah, it gets weaker. But we haven't actually seen like extinctions during reversals or anything like that, which tells us that this, again, like we'll survive, but you know, maybe we won't have Facebook, you know, like whatever. But yeah, but there's been a fun study out of Russia that actually says that, you know, during like coronal mass ejections and like really strong solar flares, like people who have pacemakers tend to have heart attacks more often because it kind of interrupts some of the electrical stuff in your body. You know, just pretty funky. So there might be a little bit more of that, but yeah, and again, we think reversals like are supposed to happen over the course of like 1,000 years, so it's supposed to take a while, but now there are these like new papers that say that the most recent one could have happened within a human lifetime. So there's like an argument within the field of paleomagnetism over like how much time this actually takes. But in general, like, we're mostly okay. You won't see a disaster movie about it, even though someone asked if I wanted to advise one once about reversals, and I was like, eh. Any more questions?
Anyone? I'd like to thank you very much for coming.
Thank you.
If everybody quits in a hurry, keep in mind